Kurt Gödel's incompleteness theorem is arguably the most important theorem in modern logic. This theorem has far-reaching implications for philosophy, theology, computer science along with mathematics. In 1931, the Austrian mathematician Kurt Gödel published his incompleteness theorem, which rocked the mathematical world. The theorem states that there are certain truths in mathematics that cannot be proven using the standard methods of proof. This has far-reaching implications, both for mathematics and for other areas of human knowledge. The first thing to note is that Gödel's theorem does not disprove anything in mathematics. Rather, it proves that certain truths exist which cannot be proved using currently accepted methods. It follows that mathematicians will have to find new ways to prove these truths, if they can be proved at all. One immediate consequence of Gödel's theorem is that it is impossible to create a single axiomatic system which can be used to prove all mathematical truths. This means that there will always be true statements about numbers that the system cannot prove. For example, the system might be able to prove that 3 plus 4 is equal to 7, but not that 3 plus 4 is a natural number. The existence of such true statements is what makes the system incomplete. Gödel's proof has profound implications for mathematics and philosophy. It might be taken to mean that mathematics is an incomplete science, subject to limitations. It also suggests that truth may be undecidable in some cases, meaning that we may never be able to know for certain whether certain statements are true or not. The practical consequences of Gödel's theorem are still being explored. Some mathematicians believe it provides a deeper understanding of the nature of mathematics and its place in the universe. Others believe it could lead to new ways of doing mathematics, or even new types of mathematics altogether. Implications of Gödel's incompleteness theorem for philosophy, computer science, theology, and economics. Gödel's theorem also might have a number of important applications outside of mathematics, in fields as diverse as philosophy, computer science, and even economics. In philosophy, Gödel's theorem might be cited in support of relativism, the idea that there is no single objective truth, but rather that truth is relative to individual perspective. For example, two people can both believe different things about the same mathematical statement, and both be right from their own perspective. In other words, what is true for one person may not be true for another. This idea has been applied to many fields from morality to politics to art. In theology, the theorem can be used to argue that certain religious beliefs are necessarily true, since they cannot be proved or disproved by any formal system of reasoning. In computer science, Gödel's theorem can be used to show that certain problems are undecidable, meaning that there is no algorithm that can always correctly solve them. For example, the famous halting problem, which asks whether it's possible to write a program that can take any other program as input and correctly predict whether it will run forever or eventually stop, is undecidable according to Gödel's theorem. As a result, programmers must often resort to heuristics, approximate methods, when trying to solve undecidable problems. Finally, economists potentially can use Gödel's theorem to study situations in which individuals make decisions based on incomplete information. For example, suppose you're considering buying a new car, but you don't know how much it will cost to maintain or how long it will last. In this case, your decision might be based on your personal beliefs about these things, which may or may not be accurate, rather than on any objective facts. Economists can possibly use Gödel's theorem to study voting systems and market competition. Overall, Kurt Gödel's incompleteness theorem has had a profound impact on many different fields of study. It continues to be an active area of research today, with new applications being discovered all the time. Complementary theorems to Gödel's incompleteness theorem. There are many theorems that are complementary to Gödel's incompleteness theorem. Some of these theorems show that certain axiomatic systems are consistent, while others show that certain formal systems are complete. The most famous theorem complementary to Gödel's incompleteness theorem is probably the Lowenheim-Skolem theorem. This theorem shows that, for any first-order language, there is a model of size continuum, that is, an infinite set on which all first-order formulas are true. In other words, any first-order theory has a model of size continuum. This fact is sometimes called the underlying infinity of first-order logic. Other theorems complementing Gödel's incompleteness theorem include the Cohen refutation of the continuum hypothesis, which shows that the continuum hypothesis cannot be proved from ZFC set theory, and Solovay's theorem, which shows that it is impossible to prove, from ZFC set theory, that every set can be well-ordered. Here are some other great math books about Gödel's incompleteness theorem. Gödel's Proof, an Incompleteness Theorem Saga, by Ernest Nagel and James R. Newman. Mathematical Fallacies, Flaws, and Flimflam, by Edward Barbeau. Gödel, Escher Bach, An Eternal Golden Braid, by Douglas Hofstadter. About Kurt Gödel. Kurt Gödel was an Austrian-American logician, mathematician, and philosopher who is widely considered one of the greatest mathematicians of the 20th century. His incompleteness theorem is a fundamental result in mathematical logic that has major implications for the philosophy of mathematics. It states that any formal system powerful enough to describe arithmetic is incomplete. There are true statements about arithmetic that cannot be proved within the system. Gödel made significant contributions to a number of other fields, including set theory, computability theory, and philosophy. He also published works on Einstein's theory of relativity and on the problem of mind and body.